use Teams and I'm just trying to get familiar with Zoom. So can you confirm if you can see the screen, please?
Yes, I can see your screen.
Okay. Okay. All right.
Yeah.
Good.
But the video, I think I cannot see the video.
Oh, you cannot see,
yeah.
You cannot see me?
Yeah.
Okay, just give me
No,
one.
no, I can now. It's it was a problem from my laptop. Okay.
Oh, okay. Okay.
Yeah.
So we have video, we have audio.
Yeah, everything is fine.
Okay. All right.
Yeah. We
Okay,
should just wait for 5 minutes until we can get more people, and then we can start. Okay.
Sure. Yeah. Yeah.
Yeah. Thank you.
Mhm. Hey guys, can you still hear me?
Yes.
Oh, okay. Thank you. Yeah, just want to make sure. Sorry.
Hello, Marco. Can you hear me? Yeah, just turn on your micro.
Yes.
All right.
Yeah.
Yes, I think now we have physics defense for another student, but the people who missed the session, they can see the session in the recording in our through our page YouTube channel. Okay, so I think we should start. And so yeah, just give me 1 minute.
Okay.
So yeah, good morning, ladies and gentlemen. So it's a great pleasure for me to introduce our speaker today. He's going to talk about the automation and future of drilling. So our speaker is the Global Drilling Engineering Manager for Weatherford Drilling Services. His oil field career began in 2001 as drilling service field engineer. He has worked at several locations, holding technical, sales, and managerial positions for major directional drill bits and expandable liner service companies. He holds a degree in mechanical engineering from Universidad de las Americas Puebla, Mexico. Ladies and gentlemen, please join me in welcoming Mr. Marco Perez. You can start.
Yes, thank you, Habib. Hi, good afternoon, everyone. Well, afternoon because I'm in Houston time, so it's already after afternoon. But good morning, good afternoon to everyone. And welcome to this session. I really appreciate your participation, and obviously, as I mentioned to Habib, thank you for the invite. I really appreciate that, as well as the introduction. Thanks for that also. So I'm really glad, as I said, to be here. And today I will be talking, as Habib mentioned, about automation and how I see the impact on the future of drilling, right? So to start with, let me just make sure. Yeah. So we have I have three sections for this presentation. The first one is a quick introduction on the topic about automation, and then the last two is our foundation for the future and future technology. Now, as a note, for obvious reasons, the last two sections, they are influenced, by Weatherford perspective. However, there are many other companies doing a lot of good work in these areas, and to be honest, to move the needle in our industry, we really need to have the collaboration from anyone in the industry. So obviously, I kept away any kind of commercialism or anything like that. But I am going to focus more into the technical side. But I think it's a good note to have in here that this is basically how we see it, but it doesn't mean that it is the only way, right? And just also, I'm not too sure how you have been handling these sessions before, but I'm pretty informal in this particular case. If you have any questions, any additional comments as we go through, and if you cannot wait to the end, then definitely we can have that conversation at that moment, or not, or if not, we can have the conversation at the end of the presentation. I'll try to wrap it up in less than an hour, so we have time for those sessions. So let's get into the topic, right? So we were talking about evolution right here in this particular slide, and the initial slide, it could be a little bit rough. I'm going to say that, right? Because before I jump into actually what is happening in the oil and gas industry with the automation and obviously the future of drilling, I want to take as a reference this video clip. It's a very short video clip, probably about 3 minutes. And I'm going to ask you two main things, right? The first one is to be patient, bear with me on this. And then the second one is to stay curious, be open-minded, and definitely look for the keywords on this particular video. And well, basically anything that we produce, that we manufacture, it is based on 4 main processes, right? And the first one is pretty much casting, and I'm going back to my background, which is mechanical engineering, casting, machining. The other one is joining, and then the last one is basically forming, right, or forging, basically. And in reality, what we are doing in the oil and gas industry is we are manufacturing wells, right? So we are manufacturing oil and gas wells, and we produce hydrocarbons in there. But in reality, well, it's a manufacturing process. Now, I chose machining because it's great similarity to drilling, right? And because of my background in directional drilling, also I see this great correlation. So I'm going to play the video now, and please let me know if you don't see it or if you don't hear the video. I really hope it goes well, and let's see. Should go. I was testing it. Yeah, I think it's coming good.
Today.
So can you confirm you can see and you heard the video, please?
Yes, I can see and hear the video.
Okay, perfect. So it will go, hopefully it will go good. So as I said, just bear with me, 3 minutes. I think we can pick good keywords here. And then after the video, I will be asking few questions.
Okay, I'm going to explain the difference between a manual machine and a CNC machine. Manual machining is dear to my heart. 20 years ago, when I got into this trade, when I didn't know anything, I was put on a manual machine. It's how I learned how to cut metal. A manual machine has hand cranks. We say hand cranking. In the Y direction in this machine, we actually rotate the handle to engage the tool into the material. In the X direction, we rotate this handle. In the Z direction, we actually lift up the spindle and lock it down. We also can engage Z-axis by raising or lowering the table. Cranking the handle actually raises the table. So now let's go look at the CNC machine. All right, so here we have a CNC machine, computer numerical controlled. So just like the manual mill, we have the same axis of movement, but now we have servo motors that are actually controlling those axes. With the CNC machine, everything is automatic, and we run off of G codes and M codes. The programs are created through a CAD/CAM system. So we take a solid model, We bring it into the CAD/CAM system, like Fusion 360. Then we actually call tools, and we call out profiles, and we run the tools around the profiles, and we create a program. Once the program is complete, it gets posted. We then send the code to the machine. The machine reads the codes, grabbing each tool and running it exactly like we did in the CAD/CAM system. You gotta grab all the tools, put them in special holders, and then you have to put the tools in the machine. You have to zero all the tools to the part, and then actually zero the part, and then you're ready to run your program. When we look at runtime, manual machining cannot compete with CNC machining. You can make this machine run lightning fast, non-stop, with no operator. Everything is automatic and efficient. It keeps my workers busy. It makes me efficient. It allows me to quote work and get those jobs so we can make parts that go on submarines, on rockets that go to space, and everywhere in between. If I didn't have a CNC machine, I would not have the work and I would not be able to employ my guys. Taking it all to another level. Boom.
All right. So I hope you enjoyed the video. Let me just go back to the slides, and while I come back to the slides, I would like to ask, what kind of keywords did you hear there in that video that will apply to what we are talking about today? Anyone?
Numerical command.
Yeah.
A program, control, code, runtime, fast, automatic, efficient.
Exactly. Automation, right? Complexity as well, right? I mean, he didn't mention it clearly, but definitely the type of pieces or components that can be manufactured on a CNC machine, it is it is far behind or far away from what we can do with the manual machining, right? Or that what they can do in the manual machining. In our world, when we are drilling wells are not getting easier. They are getting complicated every time, right? Every time we're trying to reach new targets, longer, deeper, higher temperatures, and so on. So our environment is not getting easier. It is getting more and more complex as we go. So, but as you mentioned, automation, running time. They talk about zero or setting in zero all the tools and all the pieces. So it has an additional time to set up, but then once it is set up, the running time, it is significantly shorter than if we have or if they have to manufacture that with a manual machining. So I thought it was a good illustration to see the similarities that we have and the challenges that we are facing in our industry, in the oil and gas industry, and how other industries, in this particular case, the manufacturing industry, they have been evolving, and basically being competitive and being able to survive in that business environment, right? I mean, because this evolution, it is not happening just because. There is always a reason to be more competitive, to be more efficient, and obviously to make better business for the companies. Could be operator, could be service company, whoever, but at the end of the day, it has that reason, right? This evolution is good, but there is a fundamental reason for that, right? So thank you for participating, for providing your feedback. So now digging deeper into the topic, into automation, and again making an analogy to what we have seen in the vehicles, right, that we're driving today versus what we were driving 20, 30 years ago. So obviously right now it is very common to have vehicles with, for example, ABS systems, right, brake systems, right, the anti-block system for the brakes, or cruise control, or a few other things like fuel injection, right? And if we look at the reasons behind that, is coming back to what we discussed on the previous slide, Safety, definitely it is important, and service quality, right? Service quality, it is what is going to make us more competitive. Whoever is offering better service quality, it is gaining market, it is gaining, business. And that is pretty much a must and is part of the evolution. Now, the question is this happening overnight? Well, the answer is no. As I was just saying, the evolution in the vehicles, it has been, across several years, right? It is gradual but continual. We need to keep moving. We need to keep evolving, right? Now, we many times focus on the equipment, on how we can automate the equipment. How can we make things automatic in terms of technology or hardware? But that is just one component. Any company that is not automating the processes, it is going to stay behind. The processes are equally important as the equipment that we are offering as service companies to make it as automatic as possible. And the reason for that is what I have in bullet point number 3, data-driven decisions, right? So we need to have all this data available to make the proper decision, right? We are pretty much moving away from having decisions based on experience, based on just personal experience, for example, or on our gut feeling. We need to have data. We need to have that data available to be able to make the right decision, the best decision for the business, or the best decision if it is a technical reason, the best technical reason to decide one or the other, right? And then finally, demographics. Very important, the change in generation. Over the last year or 2 years, we have seen a significant swap in the generations. We have seen in our industry, oil and gas industry, a lot of good experience leaving the industry, going and retiring or going to a different industry. And in reality, we are losing, or we have a big leak on knowledge. So knowledge sharing, it is very important. Capturing that knowledge to future generations, to continue that evolution, it is very important. So that is the other point that I want to highlight on automation and why we have this type of evolution in our industry, or we have been having this. Now, the foundation for the future. Moving into the second section of this presentation. There are, again, based on our perspective, we have 5 main pillars on this foundation for the future. The first one is data visualization. So we have been making a lot of good progress on making the data available and to be able to visualize it quickly and in the best possible way. The second one is the embedded analytics. Embedded analytics, obviously, we have the data, but we need to be able to analyze it, as I was mentioned before on the previous slide, to have data-driven decisions. The third one is basically an open architecture. We cannot just restrict our progress just to ourselves. We need to be able to connect to other parties, other systems, and be able to speak a similar language. We need to be able to understand the same thing and be able to integrate into the major workflow of the process. Then the other one is the high frequency and high density of data, right? So that is all important to be able to manage volume of data and obviously to integrate that with our analytics in there. And then the last thing is the collaboration, right? So one single platform where we can collaborate and we can exchange ideas, make decisions, all in one single platform. So those are the 5 main drivers, if you will, for the foundation of for the future, the way that we see it. Now, the first slide that I have in here is the drilling engineering quality process. So in reality, it is a simple process. It is just 4 stages, as you can read in here: the design, execute, evaluate, and optimize. So 4 stages, but if they are implemented properly, it becomes very powerful cycle. And again, it is just a simple continuous improvement plan or process in here. So if you allow me, I will just touch briefly on each of these 4 stages. And as I said before on the second slide, you know, the processes, automating the processes is equally important as automating the hardware or the technology. And this drilling engineering quality process is basically the backbone of all our services in our company. The first thing is design for success. Obviously, we need to be sure we understand the scope of work. We need to understand the history, what we have been doing before. In this case, is tailored into the drilling side. So for drilling, obviously, offset well analysis, conduct a risk assessment, and engineer the basis of design and contingencies scenarios, right? So we have, in summary, a good game plan in there. Once we have that done, then we move into the execution. The execution is divided not just in monitoring the services. Monitoring is just a visualization. I just see what is happening in there. But we need to move into the second and the third bullet point that I have in here. Avoid and mitigate drilling hazards and optimize drilling performance. Those are really the strengths of the execution phase in here. And then the evaluation is basically evaluate against our objectives. Did we meet the objectives that we set or not? That performance review, that knowledge capturing, end of well reporting, all that data, it is very, very important. And then finally is the optimize for improvement. Before we design the next job, we need to integrate all these learnings and obviously develop a much better design next time, capture all these lessons learned and so on. So all this process, it has, well, it is partially automated in our company. In some other companies, they have automated other stages in there. They have the similar approach, but to be honest, what I have seen so far in the industry is we are all working towards the same goal, trying to optimize this process. Some have more, have advanced more than others, but at the end of the day, I think we are all heading into that direction. Now,
sorry,
yes.
Marco, I have a question regarding the previous slide.
Mm-hmm.
So you said execution, and you said avoid and mitigate drilling hazards. Is it like taking decisions or just how it mitigates, like detecting the problems or taking decisions?
Right. So it is actually taking decisions. We call it interventions, right? So once we start drilling, and I have in the next couple of slides, I have an example on that. But during the execution, we have basically a roadmap, a driller's roadmap in there on how it should go sequence by sequence, right? If we have deviation from there, or if we foresee that there is a risk coming up, we need to take proactive action to make sure that we don't get into a bind. We need to probably control ROP or control ECD or circulate more or increase the flow rate or whatever the case may be. But it is an actual intervention. That's how we call it.
Okay, thank you.
Mm-hmm. Okay, so let's say once we have our game plan, we have the design phase completed. Now, what is the first thing that we need to do? Well, the first thing we need to do is start drilling, right? We need to start manufacturing the well. We need to start, digging some hole in the ground, right? So now I'm not going to expand into the directional drilling here. So I will assume, I guess, that you have some background on what is a rotary steerable system or what is a directional tool. But in reality, over the last 20, 30 years, that those directional drilling tools, they have been evolving significantly, right? So what I'm showing in here is just an example of a rotary steerable system. And the key points that we want to highlight in here are the most recent advances on this technology, right? Right now, pretty much every well that we are drilling, it requires certain degree of directional control, even the vertical wells, right? So, so pretty much in every well, we will be having a directional control tool. The key thing, or there are two main bullet points that I want to highlight in here. The first one is setting a target inclination from surface. This is similar to when you are driving in your car, driving your car, and then you press the cruise control, right? So pretty much your car is going at a certain speed that you set, and you say you maintain that. Basically, it is the same thing in here. So in this particular case, when we have a long tangent to drill, especially on extended reach drilling, for example, then we just put an automatic control in there, and then you just maintain that. The tool is going to measure the inclination and is going to do the proper adjustments as we go. Because as we know, as we're drilling different formations, we could have different formation pushes and so on, right? So that is one of the things that we currently have available. And again, many other rotary steerable system providers, they have similar controls. The second one is the proportional control that I highlight here in green. And this is very important because it impacts very heavily the borehole quality. So just to illustrate that, this is the proportional control, the green line that you see here, versus the blue or the red line, which is basically a blocky change on inclination, right? So if you imagine that you're drilling a borehole and you have these steps in there when you are trying to adjust the inclination, then the borehole quality, it is not going to be ideal. In some cases will impact more the production or the casing running or so on, but in some others probably is less, right? Like if we're drilling a surface hole, probably it's not going to have a major impact. But if you are drilling a production section or a long tangent where you have issues with torque and drag, that could create micro doglegs, micro tortuosity, and that could impact the capabilities on to achieve the target TD on that particular well. So that proportional control is not on every single rotary steerable, but in some it is in there, and it's a very important feature to have, especially for borehole conditions. Now, moving into the execution, basically, and I was talking about monitoring, that having that visualization, which is one of the first pillar that we have in the future, or in our foundation for the future. So this is just a quick example on how we can visualize multiple rigs. We can customize different alarms, different type of criteria that we need to keep an eye on. When I was doing drilling engineering a few years back, and I have to monitor 3-4 rigs, and typically the communication was just email, or they were sending you the logs. You need to open the PDF or print the PDF, looking at the log, and then drilling mechanics logs, and then identify what is, if there was an issue with the ECD, equivalent circulating density, or or with the formations that we were drilling or so on. It just took a lot of time just to do that process. Like every morning, you start looking at the rigs and how they were performing, and it was just taking a long time. Even just plotting the directional performance, you typically had in the past wall plot, and you have to plot surveys in there with a pencil and things like that. So it was just taking so much time just to do all that. Now, we have all these platforms to monitor, and not just to monitor. In this case, it's just saying automation of drilling engineering modeling tasks in real time, right? So we have all these at our fingertips, and then obviously that will make us more efficient. It will make us to move to the next stage, which was part of the question that I got before. Is it just monitoring? No, it is not just monitoring. You need to intervene. You need to make an intervention to make sure that you mitigate those risks and those hazards, right? So what I am presenting on this particular slide is how we can do that. And to do that is we need to compare the model versus the actual measurements. In this particular case, I'm illustrating three main areas that we monitor and intervene during the execution. Real-time vibration analysis. So during the design phase, we evaluate the vibrations on the VHA, right? But then during execution, many things can change, right? And so under the new conditions, the actual conditions, we run this in real time, and we validate that the drilling parameters that we are running are within, are giving us the best possible conditions for the BHA to survive the drilling environment, right? Obviously, we have downhole sensors that are feeding back all this data into the surface system to evaluate what is the lateral, vibrations that we have, torsional vibrations, axial vibrations, and so on. Now, the MSE, the mechanical specific energy, it is also a very important parameter in there. It is basically telling us how is the health of our drilling, how healthy we're drilling this hole. Are we drilling, are we using all the energy to really destroy the rock, or we are losing energy, for example, in vibrations, or due to an issue, which could be bit balling or whatever, right? And then the last point is the self-calibrating torque and drag analysis. Again, we have the model, but the model needs to be validated with actual data. And this could seem, very simple, very simple things to do, but in reality, it took a long time to get to this stage, right? Just like we have seen in the video and in the previous slides. One other example is, when we compare the estimated standpipe pressure, let's say our hydraulics model, it gives us, okay, a particular standpipe pressure under certain conditions, flow rate, mode weight, certain conditions that we have, drill pipe, and so on. But then once we start drilling, we start getting the, let's say a pretty good match with the standpipe pressure. Many times when you need to monitor 4, 5, 6, 7 rigs at the same time, you probably don't pay attention to all the little deviations between the model and the actual. That is where the alarm systems will come into play, and then that can alert the user of certain deviations. Many times we have catch drill pipe washouts on time, and we have avoid twist-offs, for example, and that, to the operator, it to me is a big value doing this exercise, because we could, prevent significant amount of NPT. Yes, it's an additional trip, but it could be worse. It could be, losing part of the BHA in the hole, especially if we have nuclear sources, measuring density and neutron data downhole. It could be a very severe impact in the operation. So when everything is going well, this could be seen as redundant. But when we prevent, when we take action, when we intervene, that is where the value comes in for this particular part. Now, following the conversation about risk mitigation and optimizing performance, let me just briefly touch on MPD. MPD is managed pressure drilling. Probably you are aware of this technology, this type of offering that we have. Now, what we have been doing with this technology, I mean, it is not new, but what it is new is how do we control this? And to control this, let me just move to the next slide. So what we have behind the intelligent control system is first the advanced hydraulics model. So that is a given. So we have software, we can calculate our hydraulics, we can estimate our bottom hole pressure. Now we need to we develop these smart control algorithms, right? So we need to have these additional or enhancement on our brain power, things that probably the human brain will not be able to detect or to analyze in the time frame that we need to. And then the integration of those algorithms into the PLC system, right? The programmable logic controller in there. So it is not just the model, it is not just the decision, the algorithm, it is the execution, the PLC in there. And then obviously we need to have a simplified user interface and alerts to the operator. So that is what is behind this intelligent control system. Now the benefits, the results, is a condition-based monitoring. That is basically the maintenance program for the equipment that we have. Reliable automated reporting. Obviously, we need to report what is happening and how we're addressing certain conditions, specifically how much back pressure we will be applying to keep the well in the condition that we want, and then remote control via single user interface. So we were talking about having just one platform, one simple architecture where we could incorporate different systems into just one. So that is what this means, the remote control via single user interface, and then data consistency in there. Now, if we go one step further, right, and we move into the deep water environments where we have a riser when we are drilling a well, let's say a semi-sub or a drill ship, for example. Now, typically, when we are in a deep water environment, everything is, it is bigger, it is heavier, it takes longer time, and time it is not your friend in there, right? I mean, you want to execute safely, but we want to execute as quickly as possible. And this is where we have developed this automated MPD riser system. Again, it is related to MPD, but as you can read here on the slide, we remove people from danger zones, mainly the moon pool. We avoid having people working in that area. So if we go back to the first or second slide, when we talk about automation, well, automation, one of the drivers for that is safety, right? And when you eliminate or remove people from that danger zone, you are pretty much reducing basically to zero that safety concern that we may have. And then the second one is reduced installation time from 2 days to 20 minutes. When we talk about a deep water operation, 2 days is a lot of money, right? And reducing that to 20 minutes, it brings significant value to the operation, right? Now that is not happening just like that, right? So obviously, as you can see on the picture on the right, there is a robotic arm, connection hub, and tools that can help us to make this more efficient, to make it more safer for our people, for the rig people, and still achieve the same objective, right? So now moving into a different area, right? So if you follow me, I'm trying to picture the different operations in the well, right? So we drill, we mitigate the risk, we visualize it, we intervene, we have MPD to, let's say, address additional risks and optimize performance. But let's say we have the hole already drilled, hole is in good shape. Now what is next? Well, the next thing that we need to do is we need to have well integrity. We need to assure that the well is going to have well integrity. Obviously it's casing, is cementing, making sure that everything is sealed down there, right? So this slide, I really like this slide because it is very simple, it's very graphical on how we evolve from mechanization to automation and the difference between those, right? So the mechanization is not, is basically you replace those human muscles with a machine, basically. But automation is when you replace the human or the use of human judgment in there, right? And this is very important when we make up casing because the integrity of that connection need to last for the well life cycle, right? So in summary, if I could, summarize this particular slide in just one word, that will be consistency. As you can see on the picture on the right, so we have all these makeup connections in here for, let's say, a casing string in here versus the traditional connections, meaning a manual connection where a human is doing that judgment on the makeup torque on that connection. So definitely with the automation of these processes, we get this consistency in there, right? Here, it doesn't mean that it is bad. We have been doing this for many, many years, but definitely there is a bigger, discrepancy on the connections in there that we are making. And the objective here is to, as I said before, to make sure that we have that integrity on the casing string and on the well, right? We don't want to lose a section or even the entire well because we have connection leaks in there, or even trying to repair those. I mean, there are few techniques that can be used to repair that, but some of those, they are just temporary solutions and not final solutions. Now, let's say we drill the well, we case the well, and it has the required integrity. Now, what is next? Well, obviously we are drilling a well, not just because, right? We're drilling the well just to put it on production or to enhance production if it is an injector or so on. We need to make it, to produce, right? So that is the objective of having this well and spending all this money, drilling this particular well. So in here, and let me just quickly check the time. So yeah, we have a few minutes. So here the objective here is regarding Industry 4, how we have adopted some of these fourth revolution concepts into production, right? Again, we are taking one of these processes that they have been optimized in other industry into the oil and gas industry. So I'm not going to get into too many details. I am going to assume that you have some idea on this Industry 4, the fourth revolution that we are living in. But the point here is how we can take those learnings, those developments, and apply those into our production environment in the oil and gas industry. So one of the main challenges that we had on that was to integrate all the enterprises systems, right? How can we integrate all of them and have just one single platform for the operator to manage assets, or manage the wells, and to obviously adjust and get the data in real time, right? Adjust the production and so on. So all that is pretty much part of the automation. Now, moving into the third section of the presentation is the future of the future technology, right? What else do we foresee?
No, yeah, no.
Go ahead. Okay. So, all right. So, how do we foresee this future technology going forward? So, let's step back a little bit, right? And let's think on what are we doing, right? So we're drilling wells, we are putting wells on production, and probably, I mean, you have an idea on how it is done in terms of planning that, right? So typically the operator, they have certain number of rigs, they have certain number of wells that they need to drill and complete in a year, for example, right? So when the drilling managers, the operations managers, they get all that information, first thing is just instinct. They try to drill as fast as possible to meet that manufacturing schedule that was set at the beginning of the year, right? So so that sometimes deviates the attention to the details of what really are going to impact the long-term goal, right? And here, in my mind, is basically drill smarter, not just faster, right? It doesn't mean that drilling faster is bad. It just means that sometimes we just focus. If you just focus on ROP or on drilling faster, you can look at the days versus depth in here. It is not going to get us to the end goal, right? It may give us a good leadway into the initial part of the sequence, the rig schedule that we have, but it's not going to get us to the point that we will efficiently meet all the manufacturing schedules, right? So as I said before, while the ROP is high, everything is looking good and there is no issue. But if we start having problems can get escalated quickly if we are not prepared to manage those contingencies. So the point here is that we need to think on how we can maximize ROP, but not just looking at the ROP, looking at all the variables that you will see on this particular image on the right. How can we target this ROP that is optimum for this particular operation based on the rig capabilities that we have, based on the well profile that we have, obviously all these parameters that you see in there, torque and drag, hydraulics, the directional tendency that we have, and we optimize that, drilling dynamics that we have, the wellbore quality, and obviously the whole cleaning pressure and ECD management. So that is where we see we are moving forward, and one of the things that we are going to we are still working on it is to increase that level of control, let's say, for the directional equipment, not just, as I said before, that cruise control that is just keeping the speed. It is also how can we steer, left or right. In this particular case, downlink the full trajectory, just like you watch on that video on that CNC machine, right? You have a program, you have a code that you loaded into the system, and then you just press go, and then it should drill the trajectory, right? So that is where the next step is. That is where the future we think it is, and by having that, we think it is going to be a major differentiator. The other one is production, right? Many times when we drill these wells, not all the wells they are laterals or they require geosteering services, but many of them they do, and especially with one well, if you can navigate through this pay zone and extend the length of that lateral and extend the exposure of that formation, it will translate into better production for the operator, right? Better well, better asset that the operator can keep. So on the traditional geosteering, we basically focus on just on the geological component of the steering. Now, what we foresee is to integrate everything in just one platform. As you can see here on this, well, this is supposed to be blue, but these boxes on the top, basically they take into account the drilling risks, what is coming up, obviously based on the drilling on driller's roadmap. The yellow ones, they are basically the geological risks. Then the green one is, once we take into account these parameters, what is the recommendation that the platform is going to give us? What do we need to do? What the operator needs to do? Drop angle in this particular case, reduce ECD, and all that recommendation is not just based on these two. It is also based on the impact on the reservoir, how it's going to be producing that particular reservoir. So those decisions right now, they are being made, those factors, they are being considered, but the cycle, it takes a long time. So that's why right now it is mainly focusing just on the geological part, but it is not focusing on the drilling or on the reservoir performance part, as you can see here. So the idea is to integrate all that and make it more automatic with these kind of guidelines for the operator, right? So getting into the conclusions here, let's see, yeah, we still have time. So the first one that I have is manufacturing and industrial practices have been leading the recent oil and gas evolution. I think there is a great similarity between manufacturing wells and manufacturing another another piece, another component, not just in the technology that is being used, but also in the processes that are being used. Unfortunately, I think in our industry, it is taking a little bit longer time. We have few roadblocks, that probably didn't, allow us to move forward at the speed that we would like to do it. Some of that is probably misconceptions of the price of doing that, or the price of evolving, and the return on investment. I think those are the main things. Now, obviously, we must continue working on future endeavors. We need to keep moving this forward. And as I said before, this is not just one service company. I think it's all service companies. Obviously, early engagements on universities just like this. I think they are crucial to keep moving this forward. At the end of the day, what we want to do, or any service company wants to deliver wells, earlier and produce more for longer. So that's why I kind of touch a little bit on what we are doing in terms of production, on production and on drilling and geosteering more efficiently, basically automating that part. Data-driven decisions, knowledge sharing, it is crucial, it is very important, and I think automating many of our processes breaks a lot of silos, a lot of a lot of information that could stay in just one person or in one laptop. And at the end of the day, I think it's going to improve consistency and that operational performance. That is very important. Now, the last point that I have in here is streamline the handover between generations through productive engagements. One example is this one that we have now. Drillbotics is very important. I believe the University of North Dakota is participating on this. I used to be part of the judges. We still have one of my global senior drilling engineers is engaged on this. Drillbotics. It is very important to exchange and close that gap between service companies, operators, and universities. Very good ideas have come up out of that. What I encourage you is to not just focus on your petroleum engineering area, explore what mechanical engineering are doing, the other guys are doing, because I think at the end of the day, we are all engineers. We're trying to get this automated and obviously a better world for everyone. So with that, I want to thank you for your time today. Again, great honor. I hope I meet your expectations. Now we still have 5 minutes or so for any questions, final comments that you may have.
Thank you so much, Mr. Marco, for your presentation. I have actually 2 questions. So based on the slide where you have presented the different factors that needs to be taken into consideration, instead of just looking for a high ROP. So are we able to enable an full autonomous decision-making while drilling system, which is capable to adapt itself for various drilling conditions? For example, being aggressive when the drilling go fast or the operation runs smoothly, and being more cautious when the downhole drilling conditions deteriorate or there is a problem with the downhole tools. This is my first question. I have another also question. What about the well control automation and the well completion? So is the system will be capable to work on the drilling mud window? And yes, these are my 2 questions. Thank you.
Right. Okay. So yeah, definitely the first one. When we talk about the ROP, it's a great approach, right? It is not with the automation and having that ability to integrate the design and the execution phase. It is not just on and off, right? Definitely there needs to be a component in there to make it automatic, but also smart enough to wherever we need, wherever we could go, with higher ROP, we should be able to do that. Now, the basis for that, I think, is what we call the driller's roadmap. In there, the driller's roadmap is basically on paper, a sequence of operations with certain parameters that we need to do, right? Now, as we are executing, and if we have deviations, as we saw on one of those slides where we compare the model versus the actual, if there is room for improvement, yes, definitely we need to go for that. So and that is also part of what we have in here. Let's see, not this one, right? So these actions coming, it is not just based on ROP, it's based on all these geological risks and the impact on the reservoir performance. So being honest, we are not there yet, but that is the let's say, the basis of design for this particular solution. Now, coming back to the let's say the MPD solution that I was presenting, yes, that is, you know, an optimization between the you know, to stay within the pore pressure window, and that is what we are doing with these systems, right? At the end of the day, not every well requires to have or has a very narrow mud weight window, but we have seen that there is a lot of good potential to use this even outside of those scenarios, and to ensure that we have a good borehole quality to allow, you know, trips in and out in even running casing in the hole, right? So I'm not sure if I answered properly. Well, the second question, the first one I think I did, but the second question I'm not too sure if that was the question, or you want to have further discussion.
Yes, if it's possible to have more details in well control, so detecting high pore pressure or a high production. So how can the system differentiate between production and kick?
Okay. Well, yeah. When we are drilling, definitely we have our, and I didn't put in here all the hardware that we use on surface to control this. Now, this is not 100% well-controlled system. This is mainly an optimization system to make sure that we have a good balance in our pore pressure environment, right? So we have a way to measure and estimate how much back pressure we can apply on this particular on a particular scenario, and that is where this PLC system will come into play, right? So obviously we put certain parameters, certain boundaries in here on what we need to have. We have obviously these control algorithms that they will require, or basically they will see how much flow we are getting back, right? How much flow we're getting in, how much flow we're getting back, and then how much pressure we need to have. Obviously, sometimes we combine this with the PWD system, which is the downhole sensor to get the annular pressure, annular pressure sensor that we have in some of the on some of the VHAs. And then based on that is how we manage to keep that back pressure, or to control that back pressure, right? And it's all via these PLC systems that we have.
Okay, thank you so much. Thank you so much.
Right.
So, do you have any other questions? I think it's two. So, just to mention that we have actually.
I have a couple of quick questions.
Go ahead.
My name is Ahmed Ismail. I'm the PhD student in petroleum engineering department at University of North Dakota. I have a question about the actually current state of art. Like, I've been following most of the presentation, but I don't know what is the current state of art for the technology, or the models. So the models or the ideas that have been presented, are they all implemented like to the industry scale, or they are still under research, or how far are we at this point?
Okay, yeah. So what I present on the second section, which is the foundation for our future, that is fully implemented, right? All this is implemented at industrial scale, as you mentioned. All this is available. All this is available. What it is not yet implemented is what is under this future technology section, right? Basically, this ROP optimization area, the geosteering area, it is not implemented yet.
Okay. A second question, I'm not sure if I missed it or it wasn't included, is how's sorry about this noise. How's machine learning and data-driven models or artificial intelligence is used in combined with like the BLC models to basically reach the decision. So as long as I understand, we are trying to replace the human decisions by machine-made decisions. So in BLC, for example, you have to write like a certain code following specific scenarios versus like machine learning or artificial intelligence, where you just learn from the data you have and your previous experience. So how are those two aspects included in the same model?
All right. So I mean, I'm just trying to rephrase the question and make sure that I am getting the question right. So what you're mentioning is, how do we replace that human judgment if it is due to data analytics or if it is actual programming? Is that right?
I'm just assuming it's both, but I'm trying to understand. This has been a question for me for a long while, like how using both concepts are put together, like using the data-driven models with just making a regular code, like a logic code. If you see this, then do this, or if the range of, let's say, ROB exceeds this limit, then and the weight on bit goes to this range, then your next step is gonna be like this. So like pre-predicted scenarios versus like data-driven models.
Right. Okay. Okay. Yeah. No. Exactly. That is good. So what I can share with you is basically that process that we discussed, right? The design, the execution, evaluate, and optimize. So what you're mentioning is, yes, we put some rules in the programming. You know, that is basically on the design phase. But many times we have, you know, even though, let's say, those rules are good, but then during the execution we encounter things that are were not captured properly in the design phase. So that's why we have that continuous improvement plan, where also this data that we are getting in real time and the learnings that we are getting in real time, they will get implemented later on in the design phase. So I think it's a combination of both. Being honest, I think they are equally important. I don't think we have one over the other. Having the data in real time and being able to learn from the data, the actual data, I think it is very important to calibrate those models. So probably I will call it more in a calibration process in there, where both of them they are equally important.
So one last question, building on what you said, is for the real-time data, do you have like a real-time driven model? So let's say based on the real-time data, you need to somewhere like modify your design. So do you wait till like the next well to include it in the design, or do you have like a real-time driven model where it would just adjust the process to fit the criteria you want to match?
Right. No, it is adjusted in real time. Now there are certain things that we cannot really change on the fly. Let's call it in that way. And then obviously we need to wait for the next well to implement it. But whatever is possible to implement in at that particular moment, we do it, and that is what I was mentioning about the interventions that we have in real time, right? So, but sometimes, you know, even though you see the improvement, it is not 100% feasible to do it on the fly.
Thank you.
Okay, do you have any other questions? So I think we can stop recording, Ahmed. And yeah,